Hi, welcome back to the lab. I'm going to do a quick video on taking a power measurement and along that a frequency measurement with a older style quote-unquote analog spectrum analyzer. The beast in question this time is the 8559A, and this differs from more modern ones because this one doesn't actually have the ability of putting any markers on it, so you basically have to read the reticule and based on the configuration and setup, actually read it directly off the screen rather than having it pop up or have the unit figure it out for you. So I'm going to go through just a quick view of the controls, a quick explanation of how to actually read the measurement off the screen. And before that, we're going to do a quick calibration using the built-in calibration signal, and hopefully that will allow you to walk up to one of these older spectrum analyzers and easily make a measurement. So let's get right in and do it. So the first thing we're going to do is just do a quick calibration. Now this requires nothing more than just the same cable that we're going to use for the actual measurement. I have a fairly long one here because my signal generator is down below a little bit and I need it. And we'll use the same cable so that we'll sort of know that things are calibrated sort of fairly well. The calibration output itself is 35 megahertz at minus 10 dBm. So we're going to put that up on the screen, and we'll just do a quick zeroing of that out so that we can actually go ahead and do the measurement and have something to compare with. I have measured the output of this, and this is with a power meter, and it is minus 10 dBm. So everything's fantastic on that side. So let's go ahead and look at the controls really quickly. We have a reference level control, frequency span, resolution bandwidth, time per division, and trigger. These are our sweep controls. We also have the ability to switch the scale on the actual screen from 10 dB per division to 1 dB per division or linear. Linear is not super useful right now for this particular measurement, so we're going to use the 10 dB per division. The two main controls that you'll see we play around with a lot, by the way, all of these are very similar on a more modern scope too. You see them on all of the more modern 8500 series and all that sort of stuff. So from HP and Agilent. You have the reference level here, which basically allows you to scale, or it sets what the top of the screen, the top of the reticule, the top line here on the screen, what power level you're referencing, or the rest of these signals on the screen are referenced to. So for example, I have this set to 0 dBm right now, which means the line on the top is 0 dBm. So if I have found a signal that happens to go all the way to the top line, where the peak of the signal touches the top line here, that signal or that tone would have 0 dBm power. And as I do this, you're going to see at the bottom we have the noise floor of the instrument, and this is the smallest signal it can detect before it starts being muddled with all the other noise within the rest of the system. So that's the first thing we have here. And of course there's also the attenuator here. You can sort of see the attenuator scale on the outside, and this unit, you push the dial in and turn it, and when the light comes on there's 0 attenuation. So we're going to put 10 dB. The little tab is broken. There should be a little tab here that sticks out so you can see where it's set to, but just know it's set to 10 dB. Now, the second control that we're interested in is the frequency. So right now it's set to full, which is the full spectrum for this particular band, and this is a multi-band instrument, so it has bands, the one that we're currently in, from 10 megahertz to 3 gigahertz, 6 to 9 gigahertz, 3 to 9 gigahertz, and so forth and so forth. We're only going to worry about the first band. It's probably the easiest one to use because there's no clutter and there's other reasons for that. So right now, with the frequency span set to full, we're seeing the entire 10 megahertz to 3 gigahertz spectrum in a single view. And of course we can adjust this so we can switch down and zoom in, if you will, or reset the frequency per division to smaller values. So right now it's set to 100 megahertz per division, and right now we're seeing this, we're centered, well, pretty much close to 0, so we're seeing everything that's coming around the local oscillator, or the DC point, if you will, of this range. But as we zoom in, quote unquote, we're going to see there's our signal. So since we have the cal signal plugged in, so we're seeing the signal that's around 35 megahertz right here. So we'll scooch right into about 1 megahertz per division, and we'll recenter that. So to actually go ahead and I'm going to ignore the time, the sweep controls for the moment, but this is just know that you can adjust the actual sweep speed either to auto, manual, which allows you to actually manually sweep it, or to some fixed setting. And there's triggers free running, which is what we're using right now, versus say single, which allows you to take a single. Might be hard to see like that, but anyway, allows you to take a single sweep at a time. So what we're going to do is we're going to calibrate this. So there's actually an adjustment set up here where you can potentially really dial in this precisely, but for our purposes I've measured this value, so I know it's minus 10 dBm. So this point here should be at this line right here. So we're going to just go adjust the fine reference level so that we know, okay, that point is now at minus 10 dBm, because our reference is set at 0, which is the top line here. So minus 10 or 10 dBm, or dB down from that would be minus 10 dBm. So now that that's set up, we're going to go ahead and we'll turn on the signal generator and go ahead and make our measurement. So from prior videos, you may remember that I have a HP 8642B signal generator, so this is what we're going to use. And we're going to just use a quote-unquote a fairly easy signal to play around with. So we'll play around with a 500 megahertz signal. So we're going to set this to, set that to 500 megahertz. And we'll set the power to minus 10 dBm. So that should correspond with the same power as our calibration, or cal signal output. So we should see it at the exact same level. I haven't modified any settings on the spectrum analyzer, so let's go up and see that. Other than the frequency span, just so that we can see the signal. So I'm going to go ahead and turn, actually I'm going to come in close-ish to 500 megahertz. That's where we expect the signal to be, so we should expect the signal to be somewhere in the center right now. I'm going to enable the output. There you go. So this is telling us a couple of things. First of all, so here's the power. The power output is a little bit lower than our calibration signal. That might be fine because, again, there's problems with setting the calibration using a cable, because losses in the cable, and dependent on the frequency, you can have more losses and less. So it makes sense that there's going to be a bit more loss at a higher frequency. If we go down to, say, a lower frequency, you probably wouldn't see it as much. But we can take a look at that in a second. So let's go do our first power measurement. So this is pretty darn close. So what we're going to do is we're going to, again, jump into about 1 megahertz. And oh, yeah, there you go. Sorry for the quick interruption. The daughter came by to see what was going on. So we're going to come into 1 megahertz per division, so we can see the signal a bit more clearly. I've recentered it, and you'll have to ignore the frequency difference here from 500 megahertz. The calibration of the frequency counter here, the center frequency, is plus minus a few megahertz. So so it's not terribly accurate, but it's good enough for my purposes. So if we look at the signal right here, we're seeing that this signal is just a little bit lower than the 10 dBm, than the 10 dBm mark. So it's, like probably about minus 12, minus 13 dBm. And that's all there is to it. Again, paying attention to what our reference level is set to. So the top line here is 0 dBm. So 10 dB below that is minus 10 dBm. Pretty simple. And that's as easy it is. On this particular model, the attenuator will actually modify the reference level as you click the attenuator, so you don't have to actually think or do any math in your head about how to factor the attenuator in. It's already built into this unit to be able to display or show you what that corrected reference level is based on the attenuator. So that's that. So let's go ahead and do another quick measurement. I'm going to key in same power, so minus 10 dB. And I'm going to key in 100 megahertz, and of course we still have something there. That should be our harmonic, of course. So let's go back and we'll go find our main 100 megahertz signal. Zoom in again to 1 megahertz. And there you go. And so we're a bit closer now. So as the frequency is going down, we're losing less power due to losses in the cable and whatnot. And yeah, that's pretty much right, bang on 10 megahertz, minus 10 dBm. And as we go ahead and say, for example, adjust the power, so I'm going to adjust it down by 10 dB, so we're now at minus 20 dB, and again, our reference level is set it to 0, so that makes sense. If I were to bump our reference level to minus 10 dBm, well, again, the signal is following that properly, because now minus 10, minus 10, minus 20 dBm, there you go. And there's not much more to say. That's how you take a measurement with one of these older style spectrum analyzers. I kind of wish the single trigger had the ability of being externally triggered. That would be really neat, because that means you can take a snapshot of something and key it into some other trigger, for example. Like, for example, use a trigger out of a scope to trigger a sweep on the spectrum analyzer if you're trying to measure something in the RF domain as something is happening in the, say, digital or analog domain. Anyway, it'd just be kind of neat, but this scope doesn't, the spectrum analyzer doesn't support that. I'm not entirely sure this line ever did, but that's life. So that's it. I hope you learned something. If you didn't, fantastic. If you did, fantastic, even better. If I made a mistake, go leave a comment and say, hey, you screwed up. Why don't you learn what you're doing and explain to me where I made my mistake. I don't mind learning at all, or finding that I made an error and correcting it. So if you wanted to see any more about this, also leave me a comment. I will do my research and try and learn a bit more, and so I can explain it in a fairly layman, beginner's kind of way. And if you're interested at all, I may do a teardown of this module, but there's a lot of fairly finicky looking RF voodoo magic in here, and it actually seems to kind of work, so I'm a little bit hesitant to touch it, but I can definitely pull out the module and at least poke around from externally. You can see a lot of the stuff in there, and I can point out some interesting things, and you can take a look at the block diagram and whatnot. So let me know. Until then, catch you later. Thanks for joining.